Can everybody hear me and see my iPad screen? If you could just type in the chat. Okay, thank you. I'll start in 3 minutes. Babe, stop texting. I can see your text on the iPad. It's okay, I muted it. So before we get started, I just want to inform everybody that so next Thursday, we'll be in person. I believe it's in Bayan 2175. And then I think that session, I'll be administering a quiz. So there won't be any content next week. Yeah, I think that's really it. I don't know if you have any questions about that. Secondly, March, let's check this real quick. So March 24th, March 24th, I'll be at a conference. So I think that week what I'm planning on doing is pre-recording the session and then posting it to YouTube. I'm not sure if anyone objects to that, but I don't really have a choice. And then I'll send out a reminder that week or the week before just to remind everybody. But I just wanted to let all of you know now about that. Anyway, so let's get started. So this week we're going to be talking about control mass and control volume analysis. So let's start with question 4. Let's start with question 1. So question 1, a piston cylinder assembly contains air initially at 2 bar, 300 Kelvin, and a volume of 2 meters cubed. The air undergoes a process to a state where the pressure is 1 bar, during which the pressure and volume have a relationship PV equals constant. Assuming ideal gas model for air, determine the mass of air, work, and heat transfer. Okay, so first things first. Actually, I'm just going to write. So part A, we want to figure out the mass of the air. So we use our handy dandy ideal gas equation. So PV equals MRT. And we just want to solve that for M. So M equals PV over RT. And this, we're just going to plug it in. So we have P is equal to 2 times 10 to the 5th Pascal times our V, which is 2 meters cubed, over over R, which is 0.287. Oh, wait a second. Yeah, 2. I think it's going to screw up the units, but times 10 to the 3rd joule over kilogram Kelvin times 300 Kelvin. I realize I just might have fudged the units, but anyway. So calculating this, you'll get 4.6576 kilograms, just rounding that out. 4.65. I know that the question is, the answer is 4.66, but I'm not sure if the TA who made this question rounded up using with one of the terms or not. But anyway, so that was pretty straightforward, just like we have been doing. So the next thing we want to do is we want to calculate the work. So the work, so just defining the work equation like we did last week, is the integral from V1 to V2 of P dV. And in this case, we're given the relationship of PV to the N equals constant. And N here equals 1. So this is assuming I think somebody asked about this last week, polyotropic process. It completely escaped my mind because I don't really ever think about these things. But yeah, so this is a polyotropic process. And for a polyotropic process, we have W equals, so actually, I'm just going to do this longhand just for everybody to see, and then I'll shorten it. So solving for P, so P equals constant over V. And then plugging that into the integral, so W equals negative integral V1 to V2 of constant over V dV. And then this equals, so I'm just going to pull the constant out. 1 V2, 1 over V dV. And this equals then negative constant times natural log V2 over V1. And you can, I think it's in your textbook, I forgot which chapter it is, but they list out all the different exponents of N and then what the respective work equation is, but I just did it longhand for you all to see. Okay, so now the issue is we need to solve for V2. As you notice, we're not given a V2. So to solve for V2, we can use P1, V1 equals P2, V2, since we know it's constant. We are given that relationship. So by that logic, V1 equals P1, V1 over P2, just doing some algebra. And then putting this back in, so we have 2 bar times 2 meters cubed over 1 bar. So notice I didn't change the pressures because the units of, I didn't change the units of pressure because the units of pressure will inevitably cancel out. Which gives you, so V2 plus 4 meters cubed. So now just going back and solving for W. So W equals negative P1 V1 times ln V2 over V1, which equals negative 2 times 10 to the 5th Pascal times 2 meters cubed times the natural log of 4 meters cubed over 2 meters cubed. And this is negative 277,258 joules, or for shorthand, negative 277 kilojoules. Let me just add a page. Oh. Nope. Nope. Okay. Okay, so continuing on. So that is so now part C. So for part C, We're going to use the energy balance equation. And what that looks like is Q plus W equals delta U. So this is heat plus work equals change in internal energy. And so we're trying to solve for Q. So solving for Q, we have delta U. Oh, sorry. What am I doing? We have Q equals delta U minus W. And I'm just going to switch to this. Actually, let me go back to and what we can say is that delta U, so change in internal energy, is just M CV delta T, since we're just dealing with the gas. Now, however, oh, sorry, no, that's correct, yeah. Yeah, however, I'm just going to preface this. So, however, since PV equals constant, delta T equals to 0. And the way that we can kind of see that is if I write P1 V1 equals M1 R1 T1, P2 V2 equals M2 R2 T2. If this equals constant and this equals constant, so first and foremost, the air isn't changing. We're not adding. We're not diluting the air. We're not changing gases. We're not. It's always homogeneous and it's always the same amount. So M and R are always the same. But by that default, then that means that the temperatures also have to be the same if P and V are constant. So what we can say is we can say that Q. So we can say that Q is equivalent to negative W because our delta U is 0, which just equals negative 277 kilojoules. So that is part A, B, and C. Yeah, so this one is fairly straightforward since I think we've done a lot of this. The only thing that was different was part C, because I don't think we've done the energy balance equation in any sessions yet. But yeah, as long as you remember that, just when you read the problem, just try to, again, like I said in the previous weeks, just try to understand what's actually happening. I know a lot of students last term were kind of stuck, what is your delta U? I can't figure it out, because there was no delta T, but then they came to realize that delta T would be 0, given the problem statement. Okay, so if there are no more questions, I'm going to move on. Isn't Q positive? Yes, wait, my bad. Q is positive. Yes, totally my bad. Sometimes I get mixed up in the signs of in the problems. Okay, so if there aren't any more questions, I'll move on to question 2. So question 2. Air is confined to one side of a rigid container divided by a partition. The other side is initially evacuated. The air is initially at P1 equals 5 bar, T1 equals 500 K, and V1 equals 0.2 meters cubed. When the partition is removed, the air expands to fill the entire chamber. Measurements show that V2 equals 2 V1 and P2 is 1/4 P1. Assuming that air behaves as an ideal gas, determine A, the final temperature in Kelvin, and B, the heat transfer in kilojoules. So I'm going to give you guys a few minutes to work on this problem. However, before we start, I just want to preface this specific problem by saying that when the partition is removed, you have to think of that state 1 and state 2 as discontinuous. So basically you have a box and it's in a vacuum and you have air on one side and a vacuum on the other, and you remove a partition. That removal of a partition, don't take it to be like work is done, kind of in a sense. So just think about it as a state 1, and then like something happens, it's discontinuous, the partition is removed, and then you have state 2. So treat the problem that way. Let's take 5 minutes and reconvene then. I'm just going to start a little bit earlier. If you're still working on the problem, that's okay. Okay, so part A, or actually rather, I'm going to write the givens first. So given, so we have P1 equals 5 bar. We have T1 equals 500 Kelvin. We have V1 equals 0.2 meters cubed. P2 equals 1/4 P1, which is 1.25 bar. V2 equals 2 V1, which equals 0.4 meters cubed. Okay, so one thing that we do know, MR is constant. So we start with air, we end with air. The mixed, so air is always air, it's constant. There's no dilution, it's always a homogeneous mixture. So what we can say with that is P1 V1 over T1 equals P2 V2 over T2. And therefore, so just solving for T2, we get P2 V2 times T1 over P1 V1. And just solving for this, actually, let me solve it down here. So solving for this, we get, so just plugging everything in, 1.25 times 10 to the 5th Pascal times 0.4 meters cubed times 500 Kelvin over 5 times 10 to the 5th Pascal times 0.2 meters cubed. So this gives us 250 degrees Kelvin. So solving for part B. So just like before, we need the energy balance equation. So that is Q plus W equals delta U. And now solving for Q, we have Q equals delta U minus W. Okay, so I was kind of trying to give you a hint before we started this problem. So no work is being done. The reason why no work is being done in this problem is because this is like a non-equilibrium process. So when the partition is removed, the process occurs instantaneously, and therefore the two states are not coupled. So W equals negative, the integral from V1 to V2, P dV does not apply in this case. We say that no work is done because in reality, delta P equals delta V equals 0. So think of removing the partition as a discontinuous process. I know it's not really clear unless you have kind of a lot of experience with this, but that's what this problem is saying. So I'm just going to write no work is being done. And if you think about it, so if it was a piston and a force was acting, or it was applying a force on something, then work would be done. But in this case, it's just removed. So no work was done in the system. So change in U equals mCV delta T, where M equals P1 V1 over R T1. So just solving for that, we have 5 times 10 to the 5th Pascal times 0.2 meters cubed over 0.287 times 10 to the 3rd joules per kilogram Kelvin times 500 Kelvin. So this gives us 0.7 kilograms of air. And so just plugging this back in, so delta U equals 0.7 kilograms times our CV. So our CV for air is 0.717 joules per kilogram Kelvin times my change in temperature. 250 is 500 Kelvin. So this equals negative 125.6 kilojoules. Okay, so that is problem 2. Fairly straightforward, minus just being able to have the intuition to know that no work is being done because something is removing the partition, but the partition isn't applying or taking a force. So yeah, so no work is being done. Does anyone have any questions about problem 2? I think a lot of these questions are kind of abstract, but I'm assuming this is what you'll see on the quiz. If you don't round the mass and you get an answer that's kind of off the measure, did you get docked for marks? Good question. I honestly don't know. So I think for the quiz, I'm grading one question and then another TA is grading another question, I believe. Or if there's 4 questions, one of us is grading a question each. So the grading, I'm not entirely sure. I personally think that if you're within a certain realm of correctness, like if you're between 5 and 10% off, I think that's fine. But as long as you just show your work, like I usually don't dock people if everything makes sense except for a few rounding errors. But I can't speak for other TAs. What is that 0.7? So that's CV. In your textbooks, let's see where are the appendices. Okay, so right here you see the CV. That's what that is. So CV for air is 0.717. Specific heat for gas, or what is that again? Showing the units of CV being kilojoules instead of joules. Potentially, let me see. I think the reason why it's not here is because, oh, maybe sure. I'd have to calculate on my calculator just to make sure. Yeah. Yeah, sure. I mean, as long as it works out. I just so for me personally, might be embarrassing, but as a PhD student, the units of R always trip me up. So I'd have to actually work this out, but I think you're right. I think it should have been in kilojoules if everything works out. Okay, so if there aren't any more questions, I'll move on to question 3. Yeah, okay. Put an extra page for question. Okay. Okay, question 3. Air enters a compressor operating at steady state with a pressure of 1 bar and a volumetric flow rate of 0.25 meters cubed per second. The air velocity in the exit pipe is 70 meters per second, and the exit pressure is 10 bar. If each unit mass of air passing from inlet to exit undergoes a process of PV to the 1/3. Now here V is not volume, V is specific volume, equals constant, determine the diameter of the exit pipe in meters. I thought this question was like particularly tricky, to be honest. But anyway, let's just take 5 minutes and reconvene. I'm just going to start this one a little bit earlier, just because I think we don't have much time. Okay, so first things first, like always, I'm going to write my givens. So P1 is equal to 1 bar. So my volumetric flow rate, which is A1V1, is equivalent to 0.25 meters cubed per second. P2 is equal to 10 bar. And V2 is 70 meters per second. So we're also given this P, and I'm going to try to differentiate my V's. But P small v to the 1/3 equals constant. And so now I'm just going to break up this problem how I would actually do it. So mass is conserved. Conserved. So therefore, m dot 1 equals m dot 2, where m dot equals rho VA. So I can rewrite this and say rho 1 V1 A1 equals rho 2 V2 A2. And so now what I want to do is I want to rewrite this equation in terms of specific volume. So using specific volume, which looks like this, we can rewrite m dot as. So for those of you who don't know, specific volume is 1 over rho, and it has units of meters cubed per kilogram. And so what that means is we can say V1 A1 over, I think it's a mu, is that a mu? mu equals V2 A2 over mu2. And now just going into that, so we want to solve for the area of the exit, so I can say V1 A1 over mu1 is equivalent to V2 times pi over 4 d2 squared over mu2. And so now just solving for d2. So d2 equals mu2 over mu1 times v1 a1 over v2 times 4 over pi. And this whole thing is to the square root. I apologize for the messiness of the square root. Oh, I didn't close my brackets. Okay, so now we need an expression for mu2 over mu1. So let's use p mu to the 1/3 equals constant. Okay, so oh, I gotta add another page. Okay, no worries. So p1 mu1 to the 1/3 equals p2 mu2 to the 1/3. So I'm just going to do some math. So we have p1 over p2 to the 1 over 1/3. So it's just a reciprocal, equals mu2 over mu1. And so this is the equation that we need. Where am I? Just add a page. Okay, so okay, so now we can rewrite the expression for d2. So d2 now equals p1 over p2 to to the 1/1/3 times V1 A1 over V2 times 4/pi. And I'm just going to do this to the 1/2 since it's easier to write to the 1/2, which is the same thing as the square root, for those of you who do not know. So now we just plug everything back in. So 1 bar for P1 over 10 bar for P2. So to the 1/1/3, or sorry, 1.3. Sorry if I kept saying 1/3. Now, we're given V1A1. That's why I wrote it in the givens as, so it says the volumetric flow rate, but you have to think about what volumetric flow rate actually means. Because, again, a lot of students last term, they got to this step and they were all confused because they were like, well, we're not given that, but you actually are. Okay, so 0.25 meters cubed per second over V2, which is 70 meters per second, times 4/pi, all to the 1/2. And you get 0.0278 meters. So I don't know. I don't really like this question. It's kind of out there because, like, for example, when I first saw it, I got really stuck because I didn't know the relationship to specific volume, or sorry, yeah, specific volume to density, or 1 over density, and I couldn't solve this problem. But yeah, after, I guess, thinking about it for a lot longer, I was able to figure it out. But I think with this problem, that was can you expand on volumetric flow rate? Sure, yeah, no worries. So area has units of meters squared, and velocity has units of meters per second. So A times V equals meters squared times meters over seconds, which equals meters cubed over a second, and that's volumetric flow rate. Does that make sense? Yeah, no worries. Yeah, again, a lot of these, it's about units, and it's about finding a relationship to transform something you're given into something else that you need. I think that really is the key to thermodynamics. And that, unfortunately, comes with time. And unfortunately, you get penalized if you don't know those kind of silly relationships off the top of your head. If I was a professor, I personally would, I don't know if I would teach it this way, but anyway. Okay, so if there aren't any more questions, let's move on to question 4, because there's, what time is it? 3:47. Okay, so question 4. Air expands through a turbine from 8 bar and 960 Kelvin to 1 bar, 450 Kelvin. The inlet velocity is small compared to the exit velocity of 90 meters per second. The turbine operates at steady state and develops a power output of 2,500 kilowatts. The heat transfer between the turbine and its surroundings and potential energy effects are negligible. Calculate the mass flow rate of air in kilograms per second and the exit area in meters squared. Let's take 3 minutes. I know it's kind of short, but I do want to have time to actually go through with it. Actually, it's not that long. You know what? Let's just take 5 minutes, and then I'll just go through it then. Okay, let's just start. All right, so as always, I like to write the givens. So given P1 equals 8 bar, T1 is 960 Kelvin, and then V1, we're just going to assume, let's take a second. So we're going to assume fairly close to 0, since it says fairly negligible. So P2 is 1 bar, T2 is 450 Kelvin, and V2 equals 90 meters per second. So recall the first law. Recall the first law, which is Q plus W equals change in internal energy plus change in kinetic plus change in potential. Now, writing this out, so Q dot plus W dot equals M dot delta U plus delta KPE plus delta PE. And writing this out further, you have M dot times CP delta T. We'll have this for that T2 minus T1 plus 1/2 V2 squared minus V1 squared plus G for gravity times the change in height. Sorry, it's supposed to be Z2 minus Z1. So we know there's no gravitational influence. V1 is significantly smaller than V2, so we're just going to ignore it. And so rewriting this equation, we get M dot Cp T2 minus T1 plus 1/2 V2 squared. So equals, oh, sorry, my bad. This was really bad of me. We know that there's no heat transfer. Does it say it's 80 potential energy effects are negligible? The steady state of the power output. Heat transfer between, yeah, so there's no heat transfer, right? Okay, I didn't make that up. Okay, so we have this equation. So now we need to solve for M dot. Sorry about that. So M dot, I'm not distracted. I'm getting a dog tomorrow, so I'm really excited. So M dot equals W dot over Cp T2 minus T1 plus 1/2 V2 squared. And just plugging everything in. So negative 2,500 times 10 to the, oh my goodness. Okay, well, let's try that. I thought I don't know, whatever. Okay. Watts over, so Cp for air, just in the back of the book where I got Cv from, you'll find Cp, 10 to the third joules per kilogram Kelvin times 450 Kelvin. Doesn't it say Ke and Pe affects a little, so we shouldn't have a V term? Where does it say heat transfer? No. Heat transfer between the turbine and its surroundings and potential energy effects are negligible. So potential energy and kinetic energy are not the same. So we do have kinetic energy, we just don't have any potential. And then it also tells us that the initial velocity, oh, okay, no worries. Minus 960K plus 1/2 This is absolutely terrible. 1/2 times 90 meters per second squared. Okay. And this will give us 4.92 kilograms per second. Okay, so that's part one. Can you guys stop texting? Okay, well, can you stop responding? Oh, okay, she responded to herself? Oh, okay. All right, so part B. So we have m dot equals rho 2 v2 a2 because we're trying to solve for a2. So the thing that we don't have though is we can't assume the density at the exit because the temperature's changed, so we can't just we can't just go to the back of the book and use a different density. So what we have to do is we have to use another kind of obscure relationship. So recall P mu equals RT. So again, using specific volume. So mu is RT over P. And then what that's going to give us is, I'll just start a new page. M dot equals V2 A2 over mu2. And then this equals V2 A2 P2 over R T2. And now just solving for A2. So we have A2 equals M dot R T2 over V2 P2. And just plugging everything back in. So we know what M dot is, so because we solve for that. So 4.92 kilograms per second, 0.287 times 10 to the third joules per kilogram Kelvin times 450 Kelvin over 90 meters per, 90 meters per second times 1 times 10 to the 5th Pascal. And this equals 0.071 meters squared. So again, kind of an obscure relationship that you'd have to know, but basically you would get to part B and realize that you have M dot, you're trying to solve for A2, you have A2, but you can't assume anything for rho 2. And so you would have to use this relationship with specific volume, between pressure, specific volume, the gas constant, and temperature to solve for A2. I don't really know what the quizzes. I guess last year the quizzes, like the questions on the quizzes weren't this obscure. They're fairly straightforward, but that probably would be advantageous to all of you to just kind of not memorize these expressions, but just think about how everything is related to one another. So don't panic if you're given something and then all of a sudden you don't have that one thing. You do have it. Just think about how you can transform one given term into another, and then plug it into the equation that you're using, and then solve for your unknowns. Does anyone have any questions? Sorry we went over time. I do have to say, I don't know how it will be in person. Oh, what kind of dog? So she's a rescue. She's a lab mix of some kind. I didn't see your question, Luke. Anyway, yeah, so, yeah, pretty excited. She is really cute, yeah. Okay, so I will see you all in person next week, really exciting. Again, so from here on out, the sessions might take a little bit longer than an hour, just because, can you scroll to question 3? Just because they are inherently a little bit longer in themselves, but I'll try to be as quick as possible. I don't know if in person will actually take 5 minutes to solve a problem, or I don't really know how it's going to be, but I'm really excited to teach in person because it's my first time teaching in person. So I'm excited to actually see all of your faces instead of floating names on a black screen. And okay, so if there aren't any more questions, good luck, study hard on the quiz. I'll upload the video on YouTube as usual, as well as the notes. I'll make sure to look over my units, and then I'll post everything tonight. Okay. Question 1, why is the constant question 1? Let's just take a look real quick. Why is the constant P1V1 again? So it just tells us in the problem that P, so right here, PV is constant. So from, yeah, okay, no worries. Yeah. Okay. Bye, have a good one, have a good weekend.